Quit all that.
Small, y'all.
Are we going? All right, problem. So here we go, problem 3. So I want to do the free body diagram first. Are you ready? What you got? Let's go. This is a bus. What do we got? So force, I hear Ross say force, gravity on bus by earth. On by language, yeah? Force what? Normal what? On bus by ground, is that fine? Okay. The bus, can we look up here and decide what's happening? Is the bus at a constant velocity or a changing velocity? So the bus is changing velocity. Okay, so that means that these horizontal forces are going to be balanced or unbalanced?
Unbalanced.
Unbalanced. That is going to be unbalanced. Yeah? Okay, great. So what are the horizontal forces? Friction and the push of the engine. Okay, when we look at this and we know that the bus is slowing, which force do you think is going to be greater, the engine push or the friction? The friction. So I'm going to say force friction on bus by ground. Okay, and I'm going to call it traction. Okay, and what I'd like you to think about is, okay, so then our engine force you said was smaller, right? So force push on bus by engine. Okay, and what I'd like you to think about is, what if the bus were on really slick ice, super slick, wet ice, no friction? Would it go somewhere? What would the wheels do? Spin, right? Okay, so that's why we have to have some friction plays a part in having it go. Do you understand? All right. Okay. Oh, you know what though? This is I don't know that I want to put traction on this one since the friction is causing the slowing. Do you know what I mean? So if it were taking off or going faster, I think I'm going to eliminate that on this one. Is that okay with you? It's certainly, if you were trying to take off, it would certainly be critical. Okay, so let's do the graph. All right? Let's do the graph. Oh, wait, we haven't done a well-labeled diagram, have we? So what's the deal? The bus? Yeah, all right. So the bus, right, is doing what?
Slowing down.
All right, so we've got a V naught of, yeah? Now, check out this 4 meters per second every second. I almost want that to be a velocity 4 meters per second, but what is it? It's an acceleration, right? So I'm going to say acceleration equals 4 meters per second, what? Squared, right? Every second, okay? So there's our thing. I don't know that I know much else. Maybe I know this, yeah? Yeah? Okay. So force diagram we've done, free body diagram. So let's do an annotated graph. What does it do? It goes from 20 meters per second. That makes 20 what? The what? The y-intercept. That's right. So I just put my numbers like this. You can do what you want to. Does that work for you? Okay, so what am I going to do? 20, I'm going from 20 to, look, I lost the board. 20 to 0. Oh, now, in how many seconds? 5. How do you know it's 5? Great. Wait a minute. 20 meters per second to 0. How long does that take? How do you know that? So I'm going to say, how do you know that? Talk about that in your small table. How do you know how many seconds? How do you know?
So it takes 5 seconds.
How do you know it's 5 seconds? All right, is everybody cool? All right, I want to go up here and I want us to remind ourselves, what equations did we get yesterday? So or on the board or whatever, we got what? V, what? And let's use them like they are in your equation sheet. So V equals I can sit here and be quiet too. Is that what we're going to do?
AT.
Plus AT. All right, that's super great. What's the next one? X.
X naught. Plus V naught. T. 1 plus 1/2 AT squared.
Right. Okay. Garrett, here, I need you here with me. Okay? All right, so that's great. Now, I want to show you that there's another one, and it comes from these two, and I'm not going to derive it for you. You can just thank me later with gifts. But I want you to have it because it will help you. Can you find this on your equation sheet? This one is special because it does not require time. Okay, so if you have a problem and you're not given time, okay, that makes this one special. Okay, these equations are used for all these are used for the constant acceleration unbalanced force model. Yeah, all these, okay? All right. Now there's one other equation we got, and we've already talked about it. And it is F. So I think I'm just going to say the other one is F net, yeah, equals what? And A, we know it can also be A is the force on a mass, right? What causes an acceleration? How much force you give to a mass, okay? So you can say A equals F net over M, okay? All right, so that's great. So this is kind of our arsenal that we have to work with. So let's go back here, and we're going to say, the first question is, how much time does it take the bus to stop? So I'm just going to say DI. What equation would you like me to use for that? What do you like?
The first one.
The first one. Okay, so you say V equals V naught plus AT. All right, so how about time, right? Does that work for you? Okay, so V is what? 20? Oh wait, that's not right. What's 20? Right, what is V?
0.
Yeah, so if you come to a stop, V is 0, so watch out for that. So 0 minus 20. Oh yeah, thanks. 0 minus 20 over, do we know acceleration?
-4.
Okay, -4. Why is it negative? Slowing, right? Slowing, okay, equals T. So that gives us what you already told me was T, which is what? 5 seconds. Okay, so that's super great. So I'm going to take my little handy dandy here, and I'm just going to get it. I'm going to go to 0 in 5 seconds. Does that work? Yes? Right, nice. Can we annotate it?
Yes.
Okay, so what's the slope?
-4.
So that's acceleration, right? Equals slope. And then what?
Area equals 50.
Displacement, which is x equals 50 meters. How'd you get that?
On the area.
1/2 base times height, right? So displacement is area. Yeah? Okay, great. All right, what's DII? Huh? What's DII? Find how far, right? What do you want to do? DII. So what equation could I use to find this? X, I hear Ross, x equals x naught plus v naught t plus 1/2 a t squared. So if you're messing around, I'm going to take you out. Do you understand? On the video, I'm going to take you out. So don't be messing around, all right? Let's take care of business. We're almost there. This is stuff that we need to do together. All right, so here we are. Do we have an x naught? Can somebody tell me, not the people who always answer, somebody new, and volunteer, what is x naught? What would it mean if this problem had an x naught? So what would it mean? Talk about the bus. Ross, you've gotten all these right. I want you to be quiet just for a second. You're doing a great job. Somebody who's sitting quiet, I need to hear from them. All right? Where would the bus start? Sure. So where would the bus start if there were a non-zero value for x naught? Where would the bus start? Give me an example. Can you use the words? The bus starts. Huh? Just give me a number. 3 coconuts?
Meters.
Okay, so can you say the sentence for me? We could use it.
The bus starts 3 meters from the origin.
Yes, yes. Was that so painful?
No.
Okay, so x naught, if it had an x naught, it would say something like, the bus starts 3 meters from the origin, and that would know that we had something. Do we have one of those? No, so that's out. Do we have a v naught? Is the bus moving when the problem starts? Yes, so let's do it. So go ahead and do it, right? We know time. Okay, so you're doing yours and I'm doing mine. My hand is in front of it for a reason. Go. I need you to be on point because you're going to be real sad over Thanksgiving if you can't do the few tiny things I'm asking you to do because you don't understand. I know it's the end. I'm really hoping you're watching The Little Mermaid in another class. Thanks. Okay. Okay. All right. Did you confirm your 50?
Yes.
Put it in your calculator and get it, please. In your phone, I don't care. Put it in and get it mathematically, please.
Oh, that one's negative.
Right?
Wait, why is it? Oh,
Look at the graph.
-4.
Yeah?
Oh. Got it.
Okay. Can you get 50 on your own with your math? Do you have a calculator, Ross, or a phone? Okay, so would you get out your calculator or your phone? Okay, do you have a phone? Let's use your phone. I felt like you probably did. Let's use your phone. Find your calculator. Juan, have you put it in on your calculator? Okay, do it. Did you actually put it in and calculate it? Okay. So, guys, stop. I need you yourself to poke with your finger on a calculator or a phone, and I need you to put the numbers in and get 50 to show up in the display yourself. So, because I think maybe I wasn't clear before, so let's try it again. Yes? Yes. Yes? Yes. I'm looking. I want eyeball confirmation.
I got 50.
Of course, right? If you didn't get 50, let us know so we can get you back into the fold. So I got 50 by saying 5 times 5, right? Squared. Maybe the most common thing is to miss the square, okay? All right, so can we go to D-I-I-I?
Yeah.
Yes.
Thank you. Been gone a little while, but you're making up for it now. I don't think the green is going to work. I'm going to set that over here in the timeout chair. And I'm going to try for the orange.
Too deep now, man.
All right. Okay, so what are we going to do? What is the net force on the bus? Tell me something I can write for net force.
Mass.
F net equals MA.
Great. F net equals MA. Do I have the ingredients to get this?
Yes.
All right, do it. Do it. Do it. And tell me what you got. Jack, are you just joking around? Okay, you said acceleration, not force. Go ahead, you're good.
Yeah, wait. That was 5,000.
Okay.
Oh, wait.
Any issues? Take a look. So if we pushed it, you could probably get help with me on another one that you wouldn't have to do by yourself. Would you like to do that?
Yes, ma'am.
Yeah?
Always.
Okay. Why don't you tell me which one you want? How about you want to look at 5? Somehow that seems like it ought to be worse, doesn't it? Because it's number 5. What's up?
Wait, how did you get, like, I understand, like, how you got the answer, but, like,
Yeah.
what does negative newtons mean?
Okay, so do you hear him asking what does negative newtons mean? So a vector, right, has direction, right? So anything that's a vector has magnitude and direction. So when something's positive, that means it's pointing its magnitude in the direction I declare to be positive. In the case of these problems, usually, was that a word? Did you hear that? Problems? Okay. In the case of these problems, usually we default to up or down being negative. Down. It's kind of default. Could down be positive one day in your life when you're an astronaut on the planet Jupiter making a colony? Yes. Okay, so usually we default to down being negative, and usually we default to positive being the direction something's moving or going to move, right? If I put the battery at the top of the incline and I let it go and I know what's going to happen, then I might make positive down the incline. Does that make sense? So if a car is moving when we start the problem, usually we declare that to be positive. So if a force were slowing it, yeah, then that force would be the other way, which is negative, yeah?
Yes.
Great call. Thanks. All right, so we're going to number 5. Did everybody get to negative 20,000?
Yes, ma'am.
Okay. So number 5 is a dog. So let's let you, I'm going to work quietly here, and you work with your table mates. See if you can get A, B, C. Confirm it with your people, right? You should have already done it, but let's confirm it. Make sure you annotated it.
I did.
Okay. Does yours look just like mine? Yeah? I want to add something. So I want a free body diagram from 0 to 8 seconds here. Yes? And then, let's see, I want another one. So I'm just going to make my box with my dot that I made up. This one is a free body diagram from 8 to 13 seconds. Okay?
So the first one.
Yeah?
Yes.
All right. Go team. We're doing number 5.
Because it's going to
I know you know. Tell me your name. Ashley? Ashley, this is your 29 for me in this room. This is your 29 for me in this room. 29, like older than you are. 29. So, what's the order, guys? What's the order of operations? First, I'm going to do a what? Then I'm going to do what? Free body diagram. Then what? Equality statements. Then math models. Okay, remember that. That's what's going to get you out of the tight spot. Want to take a look at the free body diagram? Yeah. All right, let's do it. How's about? Okay, so what do we got? Talk to me. Okay. FG on the dog, right? By the earth. Okay, somebody else? Force normal on the dog by the ground. Okay, what else you got? Okay, so I'll say force push. Is that cool? Push. And we're going to say on dog. This is the thing that moves it forward by ground. That's fine. You know, I demonstrated that kind of pushing back. Okay, and then I heard somebody say friction. Now, here's the thing. I'm just drawing them. Do you want this to be same length or different length? Same? Okay. So force. So what do you think is retarding the dog's progress? Air is good. I like that. So maybe, could be, right? Could be something else, but let's say air. That's fine. On dog by air. How about that? Okay, you've said that these are all balanced, right? So that means this must be at what? Constant. Right. So forces are balanced. That must equal constant velocity. Okay, and I don't know if I need an equation or not, but there's only one equation I know for constant velocity. What is it? Starts with an X. Equals X naught plus VT. That's it. That's it right there. VT. This is not on your equation sheet. Okay? That equation is not on the equation sheet. It's just considered almost too baby to be on there. Okay? It was your very first. Yes? Okay, so now what does it say happens after 8 seconds? The speed is increase, decrease, or stays the same? Increase. Okay, so we've got a changing velocity now, right? So help me with this. Okay, so FG, same, right? F normal, same. F, what do you figure? The air is probably the what? Same. All right, so I'm going to say that. So I'll just say F air. So what must be different if it's increasing its speed? Right? So I'll just make that a little bigger. Obviously, force push on dog. Okay. Ground. Great. So now can we make an F net? Where's the F net? Is there one up here? Is there one down here? Right or left? Right, so I'm going to say F net, right? Okay, does that make sense to you? Yes. Okay, so here we know the forces are balanced, but down here the forces are what? Unbalanced. Forces are unbalanced, and that equals, don't even think about moving, what? What? Unbalanced forces. Changing velocity, which is what? Acceleration. Nice job, guys. Hold on a second. Don't even move. Let me hit the button.